Space is not cold. I know that sounds wrong. I know that everything you've ever heard about the universe, every documentary, every textbook, every offhand comment from a science teacher, has drilled a single image into your head: an icy, black, frozen void, astronauts bundled in thermal suits, frost on windows, the great frozen void. And there is truth in that image. Parts of space are cold, brutally, punishingly cold. But the full picture is something so much stranger, so much more violent, and so much more unsettling than the neat little story you were given. Because the universe doesn't sit at one temperature. It swings between extremes so far apart that the word temperature almost stops meaning anything. And the hottest parts of that spectrum, the parts nobody mentions on those calm, soothing space documentaries, make the surface of the sun look like a cup of lukewarm tea. Let's start with the lie. Or rather, the half-truth that became a lie through repetition. The number everyone quotes is 2.7 Kelvin. That's negative 270.45 degrees Celsius, roughly 2.7 degrees above absolute zero. The figure comes from the cosmic microwave background, the faint electromagnetic afterglow of the Big Bang, which fills every cubic centimeter of the observable universe. Satellites like COBE and the Planck Observatory have measured it with stunning precision. It's real, and it leads to a perfectly reasonable conclusion. The universe is a freezer, reasonable, and deeply misleading, because that number describes the temperature of the background radiation field, not the temperature of what's actually floating around in space. The particles, the plasma, the superheated gas, the accretion disks around black holes, the stellar cores, the relativistic jets screaming across galaxy clusters. Those temperatures range from near absolute zero to trillions of degrees. The 2.7 Kelvin figure is like quoting the average wealth of a room containing 1,000 penniless people and 1 trillionaire. Technically accurate, practically useless. To understand why this distinction matters, you need to rethink what temperature means in a vacuum. And this is where your instincts, built across a lifetime at the bottom of a thick atmosphere, will betray you. On Earth, temperature is a sensation. You step outside on a January morning, and cold air hits your face. That sensation is molecular. Billions of nitrogen and oxygen molecules crashing into your skin every second, each collision transferring a tiny fraction of your body heat outward. Faster molecules, hotter air, more molecules per unit of volume, faster heat loss. Temperature, as your body understands it, is about the rate of energy exchange between your flesh and your environment. In the vacuum between worlds, there's almost nothing to exchange energy with. Interplanetary space near Earth holds about 5 to 10 particles per cubic centimeter, mostly protons and electrons, streaming off the sun. Interstellar space is thinner, roughly 1 atom per cubic centimeter. The great intergalactic voids can drop to 1 particle per 10 cubic meters. The air you're breathing right now packs approximately 25 billion molecules into every cubic centimeter. The gulf between those numbers is so enormous that comparing them almost feels dishonest. What this means, practically, is striking. An astronaut floating in deep space, shielded from all starlight, would not feel cold. Not immediately, not for hours. Their body would shed heat only through infrared radiation, the slow, patient emission of photons from their skin. No air molecules to conduct heat away. No wind to accelerate the process. just the gradual glow of their own warmth, bleeding outward into nothing. During that slow bleed, they'd actually face a more pressing danger from overheating. The human body generates heat constantly through metabolism, and in a vacuum, that heat has nowhere efficient to go. Inside spacesuits, fogged visors, and soaked cooling garments are a well-documented problem. Not because space is hot, but because the body is, and the void provides no relief. Space doesn't freeze you. Space doesn't cook you. Space is empty. And emptiness, it turns out, is its own flavor of lethal. Now, those sparse particles drifting through the vacuum, the ones I just said were too few to transfer meaningful heat. Their individual temperatures would stagger you. The solar wind, that constant stream of charged particles flowing outward from the sun, carries proton temperatures of 100,000 to 300,000 degrees Celsius. In the solar corona, the sun's wispy outer atmosphere, temperatures blow past 1 million degrees. That single fact confounded physicists for most of a century. The visible surface of the sun, the photosphere, sits at about 5,500 degrees. The corona, floating above it like a translucent halo, runs hundreds of times hotter. It's as if you walked away from a campfire and the air kept getting warmer with every step. The current best explanation involves the sun's magnetic field lines twisting, tangling, and violently snapping in a process called magnetic reconnection, releasing enormous bursts of energy into the corona. 60 years of research, and the full picture still isn't complete. But the corona is our stellar backyard. What happens farther out? Our entire solar system sits inside something called the local bubble, a cavity in the interstellar medium roughly 300 light-years across. The gas filling this bubble is not cold. It's been heated to approximately 1 million degrees by a series of supernova explosions that went off in our galactic neighborhood between 10 and 20 million years ago. Stars that no longer exist blew themselves apart, and the energy they released carved a hot, low-density pocket into the surrounding galaxy. We drift through it right now, at this moment, surrounded by million-degree gas on all sides. You can't feel it. The gas is so thin that the total thermal energy in any given volume is negligible. A cubic meter of million-degree interstellar gas carries less total heat than a cubic meter of air at room temperature. The particles move ferociously fast. There just aren't enough of them to matter. This is the distinction that cracks open the entire thermal story of the universe. Temperature versus heat. Temperature measures how fast individual particles are moving, their average kinetic energy. Heat measures total thermal energy in a volume, which depends on both speed and particle count. You can have furiously high temperatures with almost no heat if particles are scarce. A single spark from a campfire is technically at thousands of degrees. It lands on your skin and you barely flinch. A pot of boiling water is only at 100 degrees. Stick your hand in that, and you're going to the hospital. Speed per particle versus total particles. That's the whole game. In space, you're surrounded by sparks, scorchingly fast, vanishingly rare, and individually harmless. This sounds abstract. It is not. This distinction is the single reason that spacecraft thermal engineering is one of the hardest problems in the history of engineering. It is why the International Space Station requires a cooling system that weighs thousands of kilograms. And it is why space kills you in ways that appear to contradict each other. The station orbits Earth every 90 minutes, 45 minutes in direct sunlight, 45 in Earth's shadow. When the sun-facing hull absorbs solar radiation, surface temperatures climb to 121 degrees Celsius. When the station crosses into darkness, those same surfaces plummet to negative 157 degrees, a swing of nearly 280 degrees, 16 times per day. Every day, without exception. At any given moment, one side of the station is being blasted by unfiltered solar radiation, while the other side radiates heat into the void. The thermal control system handles this with ammonia-filled coolant loops, heat exchangers, and massive radiator panels that constantly shuttle energy from the hot side to the cold side. It never rests. It can't. Remove it, and the crew doesn't survive a day. Not because of heat, not because of cold, because of both, simultaneously, on opposite sides of the same spacecraft. The same thermal whiplash follows you to every surface in the solar system. On the Moon, equatorial daytime temperatures hit 127 degrees Celsius. Night crashes to negative 173. The lunar day lasts about 2 Earth weeks, so the surface bakes for 14 straight days and then freezes for another 14. The regolith is such a powerful insulator that the top centimeter can be scorching, while just a few centimeters below, the soil is dramatically cooler. No air redistributes anything. No convection. No wind. Temperature on the Moon is purely a function of whether the sun is currently shining on that exact patch of dust. During the Apollo missions, engineers had to account for temperature differences of over 250 degrees across a single spacecraft sitting on the surface. The sunlit side of the lunar module could be hot enough to burn skin through a glove, while the shaded side was cold enough to make metal brittle. And the astronauts working outside had to contend with their own thermal management. A spacesuit in direct lunar sunlight absorbs so much radiation that the cooling system becomes the critical life support component, in some situations more urgent than the oxygen supply. Mercury amplifies everything to an almost absurd degree. Its daytime surface hits 430 degrees Celsius, hot enough to melt lead, hot enough to melt zinc. The night side plunges to negative 180. That's a total range exceeding 600 degrees on a single planet. Mercury rotates so slowly that a solar day lasts 176 Earth days. Every point on the surface endures roughly 88 days of continuous, relentless solar heat-in, followed by 88 days of darkness, colder than any naturally occurring environment on Earth. The boundary between the two, the terminator line, is a thermal cliff. Temperatures shift by hundreds of degrees over just a few kilometers of cratered rock. No human will stand on Mercury in our lifetimes. The problem is not getting there. The problem is surviving there. The planet hits you from both ends at once, simultaneously threatening to cremate you and freeze you, depending on nothing more than which direction your body happens to be facing. All of these extremes run on one mechanism: thermal radiation. In the absence of an atmosphere to scatter and redistribute energy, radiation is the entire game. The sun pumps out approximately 3.8 times 10 to the 26th power watts. Every surface in the solar system sits in some fraction of that deluge. Face the sun, and you absorb photons. Turn away, and you radiate your own heat into the void, with nothing returning to replace it. There is no buffer, no thermostat, no gentle averaging. Just photons in versus photons out, and the merciless math of which side wins moment to moment. This is why every spacecraft that has ever flown is draped in multi-layer insulation, those distinctive sheets of gold and silver foil that make probes look like they were wrapped for a particularly unusual birthday party. Each reflective layer bounces infrared radiation. The vacuum gaps between layers block conduction. Together, they hold the thinnest possible line between an instrument's survival temperature and the extremes outside. Remove the foil, and the mission ends. And then there's Venus. Venus introduces the opposite version of the problem. Venus is the hottest planet in the solar system, and not because it's the closest to the sun. Mercury holds that distinction. Venus wins because its atmosphere, a suffocating blanket of carbon dioxide 90 times denser than Earth's, laced with sulfuric acid clouds, traps incoming solar energy so efficiently through the greenhouse effect that the entire surface has been cooked to 465 degrees Celsius, day and night, equator and pole. It barely varies. Venus achieved thermal equilibrium in the worst imaginable way. It became a planet-sized oven with no off switch. In vacuum, the thermal challenge is that heat has nowhere to go. On Venus, the challenge is that heat has nowhere to escape. The thick atmosphere conducts heat through every surface, every joint, every material, relentlessly. Insulation doesn't solve the problem, because insulation only slows heat transfer. It doesn't stop it. Active cooling doesn't work, because there's nothing cooler to dump the heat into. The surrounding air is already at 465 degrees. There is no trick. There is only time. When the Soviet Union landed Venera probes on the surface in the 1970s and 1980s, the spacecraft survived between approximately 50 and 127 minutes before the heat killed their electronics. No lander has ever operated longer, not because of a design flaw, because Venus is patient, inexorable, and total. The heat gets in eventually. It always does. NASA's Da Vinci mission concept acknowledges this reality. The probe is designed to study Venus during its descent through the atmosphere, collecting data on the way down, photographing the landscape, and sampling the chemistry, knowing that the surface will destroy it shortly after it arrives. It is an engineered concession. Venus is not a world we visit. It's a world we fall into briefly, grab what data we can, and then lose. Venus and the vacuum of space represent opposite poles of the same fundamental problem. In vacuum, your spacecraft can't shed heat fast enough. On Venus, your spacecraft can't keep heat out long enough. Both environments are lethal. Both exploit the same physics of energy transfer, and both demonstrate something unsettling about the universe. The range of temperatures compatible with human technology, let alone human biology, is vanishingly narrow compared to what the cosmos routinely produces. Imagine, for a moment, standing in the shadow of a crater near Mercury's North Pole, not the equator, not the sun-blasted lowlands, one of the permanently shadowed craters that never sees sunlight because Mercury's rotational axis has almost no tilt. Inside those craters, temperatures drop to about negative 200 degrees Celsius, cold enough to trap water ice. And NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, confirmed it. There is ice on Mercury. Billions of kilograms of it, hiding in frozen shadows on the closest planet to the sun. Right next door, geologically speaking, to surfaces hot enough to melt tin. The hottest and coldest environments in the inner solar system exist on the same world, separated by nothing more than whether sunlight touches the ground. That is what temperature means in a place without air. The thermal hostility of space has shaped every spacecraft we've ever built, often in ways that aren't obvious from the outside. Consider the Voyager probes. Voyager 1 and Voyager 2 launched in 1977 and are now the two most distant human-made objects in existence. Voyager 1 is roughly 24 billion kilometers from the Sun. At that distance, solar energy is negligible. The surrounding interstellar medium, while threaded with million-degree gas from the local bubble, is too thin to transfer any heat. The probes are cooling, slowly, inexorably cooling. Their power comes from radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium-238 into electricity. When the probes launched, each generator produced about 470 watts of thermal power. Today, nearly 50 years later, the plutonium has decayed enough that output is down to roughly 250 watts and falling by about 4 watts per year. Those generators serve double duty. They provide electricity for the instruments, and their waste heat keeps the spacecraft warm enough to function. As power drops, the thermal margin shrinks. Engineers have had to shut down instruments and heaters one by one to keep the remaining systems above their minimum operating temperatures. When the generators can no longer produce enough heat, the last instruments will freeze, and the Voyager probes will become silent, drifting artifacts, cooling toward the temperature of the interstellar medium over thousands of years. Eventually, over millions of years, they'll reach thermal equilibrium with their surroundings, whatever that happens to be at their location. A temperature determined by the balance between the faint glow of distant starlight and the slow radiative cooling of a metal shell in the void. It won't be absolute zero. It'll be a few degrees above it, cold enough that the molecules in the spacecraft's structure will barely vibrate. There was something quietly devastating about that. 2 machines built in the 1970s, carrying golden records encoded with the sounds and images of Earth, drifting through interstellar space, gradually losing the heat that keeps them alive. The thermal death of the Voyager probes isn't dramatic. It's slow, predictable, and absolutely certain. Every year, a little less power, a little less warmth, a little less ability to whisper data back to a planet 24 billion kilometers behind them. They're not going to crash. They're not going to explode. They're going to get cold. And then they're going to go quiet. The thermal challenges of deep space are not only about cold, either. The Parker Solar Probe, launched in 2018, is flying closer to the Sun than any spacecraft in history. At its closest approach, it passes within about 6.1 million kilometers of the Sun's surface, deep inside the corona. The solar radiation at that distance is roughly 475 times more intense than what we experience on Earth. The sun-facing side of the probe's heat shield reaches temperatures of about 1,370 degrees Celsius. That's hot enough to melt steel. It's hot enough to melt many ceramics. The heat shield is made of a carbon composite foam, sandwiched between 2 carbon fiber plates, and coated with a white ceramic layer that reflects as much solar energy as possible. Behind it, the spacecraft's instruments and electronics sit at roughly room temperature, an object experiencing 1,370-degree heat on one side while maintaining 30 degrees on the other, with only a few inches of engineered material between them. The Parker Solar Probe is, in a real sense, the most extreme demonstration of spacecraft thermal engineering ever attempted. It is a machine deliberately flying into a furnace, and the only thing keeping it alive is a shield designed to manage a temperature gradient steeper than almost anything found in nature. The probe's mission has already produced extraordinary results. It has directly sampled the solar corona, the first human-made object to do so. It has measured the magnetic field structures called switchbacks that may help explain why the corona is so much hotter than the surface. And it has confirmed that the boundary of the corona, the Alphen surface, is not a smooth sphere, but a wrinkled, dynamic boundary that the probe has crossed and recrossed multiple times, alternating between the corona and the solar wind in the same orbit. Every one of those measurements was made possible by a heat shield that keeps a few centimeters of insulation between 1,370 degrees and room temperature. The margin between discovery and destruction is, quite literally, the width of a dinner plate. This brings up a thought that I find genuinely unsettling. Every human achievement in space, every observation, every landing, every sample return, has been accomplished within an absurdly narrow thermal band. The electronics that run our spacecraft operate between roughly -40 and 85 degrees Celsius. The humans inside them survive between about 15 and 30 degrees. The batteries, the solar cells, the optics, the reaction wheels, every component has a temperature range it must stay within, and those ranges are laughably small compared to the environments we're sending them into. Our entire technological civilization in space is a series of tiny, warm boxes drifting through an environment that casually produces temperatures spanning a dozen orders of magnitude. And every one of those warm boxes is a triumph. A human-engineered pocket of survivable temperature, surrounded on all sides by conditions that would destroy it in seconds without the right insulation, the right coatings, the right coolant loops, the right orientation. When the Apollo astronauts walked on the moon, they existed inside a thermal envelope, roughly 2 inches thick, between their skin and an environment that could simultaneously burn and freeze them. When Webb observes a galaxy 13 billion light-years away, it does so from behind a sun shield thinner than a credit card, maintaining a temperature difference of over 300 degrees across a gap you could reach across with your arm. Honestly, the fact that any of this works at all is one of the most impressive things our species has ever done. Not because the physics is mysterious. We understand heat transfer very well, because the engineering margins are so thin and the consequences of failure are so total, and we've done it anyway, dozens of times, across billions of kilometers, for decades. Every functioning spacecraft is a monument to the idea that you can carve a livable niche out of the most thermally hostile environment imaginable if you're clever enough and careful enough and stubborn enough. And that, when you think about it, is what Earth is too. A warm box, a pocket of tolerable temperature in a universe that has no particular interest in providing one. The atmosphere traps heat. The magnetic field deflects charged particles from the sun, The oceans distribute thermal energy across the surface. The rotation period is short enough that no hemisphere bakes or freezes for too long. Every piece of that system is the result of specific physical conditions: the planet's mass, its distance from the sun, its composition, its spin, its magnetic dynamo, and none of them were guaranteed. They just happened. And inside the warm pocket they created, carbon chemistry did its thing. Before we move on to the stars themselves, there's one more thermal phenomenon in our own stellar neighborhood worth pausing on. Something happening right now, invisibly, that connects every planet and moon in the solar system to the thermal violence of the larger universe. The sun does not emit a steady, constant stream of energy. It flares. Periodically, the tangled magnetic field lines on the sun's surface snap and reconnect, releasing bursts of radiation and charged particles called solar flares and coronal mass ejections. A major solar flare can release the energy equivalent of billions of nuclear weapons in a matter of minutes, heating localized regions of the corona to tens of millions of degrees, and hurling billions of tons of magnetized plasma outward into the solar system at speeds of several million kilometers per hour. When those ejections reach Earth, usually 1 to 3 days after leaving the sun, they slam into the magnetosphere and compress it. The charged particles funnel along magnetic field lines toward the poles, exciting atmospheric gases and producing the aurora borealis and aurora australis, beautiful from the ground, dangerous in orbit. A severe geomagnetic storm can damage satellites, disrupt power grids, and expose astronauts to radiation doses that exceed safe limits in hours. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, induced electrical currents strong enough to set telegraph offices on fire. If an event of that magnitude hit today, with our global dependence on satellites and power infrastructure, the economic damage could reach into the trillions of dollars, all of it caused by the sun's thermal instability, by magnetic energy converting to heat in the corona and flinging that heat across 150 million kilometers of vacuum. And the sun is a calm star, a well-behaved, middle-aged, average-mass star. There are stellar objects in our galaxy that make the sun's worst tantrums look like a candle flickering in a breeze. Magnetars. A magnetar is a type of neutron star with a magnetic field roughly a quadrillion times stronger than Earth's. That's 1,000 trillion. The magnetic field is so intense that it distorts the shape of atoms, stretching them into thin cylinders aligned with the field lines. At the surface of a magnetar, the magnetic energy density exceeds the energy density of the matter itself, meaning the field contains more energy per cubic centimeter than the ultra-dense neutron star material beneath it. Magnetars are unstable. Their crusts crack and shift under the stress of the magnetic field, and when they do, they release bursts of X-rays and gamma rays of terrifying intensity. These are called magnetar flares, and the most powerful ones are classified as giant flares. On December 27th, 2004, a giant flare from the magnetar SGR 1806-20, located about 50,000 light-years away on the other side of our galaxy, hit Earth with enough energy to measurably ionize the upper atmosphere and briefly saturate every gamma-ray detector in orbit from 50,000 light-years away. If that magnetar had been within 10 light-years, roughly the distance to a few of our closest neighboring star systems, the radiation would have been catastrophic for life on Earth. And the flare lasted less than a second. The surface temperature of a young magnetar can reach roughly 10 million degrees. That is hotter than the core of many ordinary stars. A single compact object, 20 kilometers across, glowing at temperatures that dwarf our sun's interior, and it's producing magnetic fields so powerful that they could erase the magnetic strip on your credit card from halfway across the solar system. That last detail sounds like a joke. It is not. If you could somehow approach a magnetar, which you absolutely cannot and should not, the experience would be surreal and immediately fatal in ways that have nothing to do with temperature. At a distance of about 1,000 kilometers, the tidal forces, the difference in gravitational pull between your head and your feet, would stretch your body apart. Before that happened, the magnetic field would have already disrupted the electron clouds around every atom in your body, fundamentally altering your biochemistry at a distance. The intense X-ray flux from the surface would irradiate you lethally in microseconds. And the surface temperature of 10 million degrees would be the least of your concerns, because you would have been killed by at least 3 other mechanisms before you got close enough for the heat to matter. The universe has no shortage of objects that are thermally extreme. What varies is the flavor of that extremity. White dwarfs, the remnant cores of dead sun-like stars, have surface temperatures ranging from about 100,000 degrees, for the freshly exposed ones down to roughly 4,000 degrees, for those that have been cooling for billions of years. They represent, in a sense, the long thermal afterlife of ordinary stars, slowly radiating away the heat they accumulated over billions of years of nuclear fusion. A white dwarf is a stellar ember, still glowing, but with nothing left to burn. Given enough time, trillions of years, it will cool to the temperature of its surroundings and become a black dwarf, a hypothetical object so cold and dark that it is essentially invisible. None exist yet. The universe is too young. Brown dwarfs, objects too small to sustain hydrogen fusion, but too large to be planets, occupy a strange thermal middle ground. Their surface temperatures range from about 2,000 degrees for the warmest, down to near-room temperature for the coldest. A class of objects called Y-dwarfs. Some Y-dwarfs have surface temperatures below 25 degrees Celsius. You could, in principle, stand on one and not be burned, though you'd face other problems, like the crushing gravity and the complete absence of a surface to stand on. The idea that there are star-like objects out there cooler than a summer day on Earth is one of those facts that quietly rearranges your sense of what the universe is. The thermal census of the universe, if you could take one, would reveal a distribution so extreme and so skewed that no bell curve could contain it. On one end, the cosmic microwave background at 2.7 degrees above absolute zero. On the other, the Planck temperature at 142 million degrees. And scattered between those endpoints, every conceivable temperature, realized somewhere, in some object, at some moment, in the vast ongoing process of the cosmos cooling from its initial state. So far, everything I've described has been about objects responding to heat, absorbing it, radiating it, shielding from it, succumbing to it. Now let's talk about where that heat comes from in the first place, the engines that drive the thermal story of the universe. The stars. Our sun, at 5,500 degrees on the surface and 15 million at the core, is a spectacularly ordinary star. A yellow dwarf of middling mass, fusing hydrogen to helium at a steady, predictable rate, with about 5 billion years of fuel left. In the gallery of stellar objects, the sun is a landscape painting hanging quietly in a hallway full of burning buildings. Blue supergiants burn at surface temperatures of 10,000 to 50,000 degrees. They exhaust their fuel in a few million years, living fast, shining hard, and dying violently. Wolf-Rayet stars, massive stars in the final throes of evolution that have blown off their outer hydrogen shells, expose their cores directly to space at temperatures exceeding 200,000 degrees. They pour ultraviolet radiation into the surrounding interstellar medium so intensely that they ionize gas clouds light years away. Surfaces, though. Surfaces are the mild part of the story. Inside a massive stellar core, nuclear fusion progresses through a sequence of stages, each one burning heavier elements at higher temperatures. Hydrogen fuses to helium at about 15 million degrees. Helium to carbon at 100 million. Carbon burning requires roughly 500 million. Neon ignites at 1.2 billion. Oxygen at 1.5 billion. And silicon, the final act, burns at approximately 2.7 billion degrees Celsius. What makes this sequence terrifying is the compression of time. A massive star burns hydrogen for about 10 million years, helium for 1 million, carbon for roughly 1,000 years, neon for about 1 year, oxygen for a few months, and silicon? Silicon burning lasts about a single day. In 24 hours, the core fuses silicon into iron at nearly 3 billion degrees, building a growing sphere of inert iron ash at its center. Iron is the dead end of stellar fusion. Fusing iron absorbs energy instead of releasing it. Once the iron core exceeds approximately 1.4 solar masses, the only force holding it up, electron degeneracy pressure, simply fails. The core collapses entirely in under 1 second. Thousands of kilometers of stellar material rushing inward at roughly a quarter of the speed of light. It compresses. It rebounds. A shock wave erupts outward through the outer layers of the star. Temperatures in that shock wave reach between 20 billion and 100 billion degrees. For a handful of seconds, one dying star outshines the combined light of every other star in its galaxy. This is a core collapse supernova. The explosion forges elements heavier than iron, gold, platinum, uranium, and flings them into the surrounding space. Every atom of gold that exists on Earth was born in a blast like this, at temperatures so far beyond human experience that no analogy can bridge the gap. In February 1987, a blue supergiant in the Large Magellanic Cloud, a small galaxy orbiting our own, about 168,000 light-years away, detonated. It was designated Supernova 1987A, and it was the closest observed supernova since Johannes Kepler documented one in 1604. Underground neutrino detectors in Japan, at the Kamiokande Observatory, and in the United States, at the IMB detector in Ohio, caught approximately 24 neutrinos from the collapsing core. 24. From an event that released more energy in 10 seconds than our sun will generate across its entire 10 billion year lifetime. Nearly every particle the explosion produced passed through the Earth without interacting with a single atom. a supernova is the most energetic single event in the modern universe. It is not the hottest. When two neutron stars merge, temperatures reach levels that leave supernovae behind entirely. Neutron stars are the compressed remnants of massive stellar cores that didn't quite have enough mass to collapse into black holes. They cram about 1.4 to 2 times the mass of our Sun into a sphere roughly 20 kilometers across. A teaspoon of neutron star material weighs approximately 1 billion tons. Surface gravity is about 200 billion times Earth's. If you could somehow stand on one, and you cannot, you would be crushed into a film of atoms thinner than a sheet of paper before your nervous system could register what was happening. In a binary neutron star system, the two objects spiral inward toward each other over millions of years, gradually losing orbital energy by radiating gravitational waves. Einstein predicted these waves over a century ago. LIGO detected them for the first time in 2015. When the neutron stars finally touch, the merger unfolds in milliseconds. Temperatures at the collision point exceed 300 billion degrees. Certain computational models suggest the peaks may surpass 1 trillion. At those temperatures, the building blocks of matter come apart. Protons and neutrons, the particles that make up every atomic nucleus, dissolve into their constituent quarks and gluons. The result is quark-gluon plasma, the same exotic state of matter that filled the entire observable universe during its first microsecond of existence, before things cooled enough for familiar particles to form. On August 17th, 2017, the LIGO and Virgo observatories detected gravitational waves from a neutron star merger, roughly 130 million light-years from Earth. Within 1.7 seconds, the Fermi Gamma Ray Space Telescope registered a short gamma-ray burst from the same region of sky. Within hours, optical and infrared telescopes identified the fading afterglow. The event, GW170817, became the most intensely studied astrophysical event in the history of science. Over 70 observatories contributed data. The observations confirmed a decades-old theory. Neutron star collisions are where the universe produces its heaviest elements. The gold in a wedding band, the platinum in a catalytic converter, the iodine your thyroid needs to function, forged in the milliseconds where temperatures dissolve the structure of atomic nuclei. We've recreated this state of matter on Earth, briefly, at enormous expense, and in miniature. At the relativistic Heavy Ion Collider at Brookhaven National Laboratory, and at the Large Hadron Collider at CERN, physicists accelerate gold or lead ions to velocities approaching the speed of light and slam them together. In the collision zone, for approximately 10 to the negative 23rd seconds, in a volume smaller than a proton, temperatures reach 4 to 5.5 trillion degrees Celsius. That is roughly 350,000 times hotter than the core of the Sun. It is the hottest temperature ever produced by human beings. What they found in that tiny furnace surprised everyone. The quark-gluon plasma behaves as a nearly perfect liquid, not a chaotic spray, not a gas, a liquid flowing with the lowest viscosity to entropy ratio of any substance ever measured, smoother than water, smoother than superfluid helium, smoother than anything else that has been observed in any laboratory, anywhere. The hottest substance in the universe turned out to be the most frictionless. No theoretical model predicted this before the experiments ran. When I first read about that result, it stopped me cold. It's one of those moments where the universe quietly reminds you that it doesn't owe you intuitive answers. Let me take you somewhere else before we go further. Somewhere that demonstrates just how violently temperature behaves when gravity gets extreme. Black holes. A black hole itself, the singularity and its event horizon, is paradoxically one of the coldest things in the universe. Stephen Hawking showed in 1974 that black holes should radiate thermal energy through a subtle quantum mechanical process at the event horizon. The temperature of that radiation is inversely proportional to the black hole's mass. For a stellar mass black hole, say 10 times the mass of the Sun, the Hawking temperature is about 0.00000006 Kelvin, 6 billionths of a degree above absolute zero, trillions of times colder than the cosmic microwave background, immeasurably cold. For a supermassive black hole, the kind sitting at the center of most galaxies with millions or billions of solar masses, the temperature is even lower. In any practical sense, the black hole itself is among the coldest objects that can exist. The space around a black hole is an entirely different matter. When gas, dust, or shredded stellar material falls toward a black hole, it doesn't drop straight in. Angular momentum forces the material into a spiraling disk, an accretion disk, and as the gas spirals closer to the event horizon, it compresses, rubs against itself, and heats up through friction to extraordinary temperatures. The inner edge of an accretion disk around a stellar mass black hole reaches tens of millions of degrees. The material glows in X-rays. Around a supermassive black hole, the temperatures are somewhat lower per unit area because the disk is spread across a much larger space. But the total energy output is beyond anything else in the universe. A single supermassive black hole, actively feeding on its surroundings, can outshine the combined light of every star in the galaxy that houses it. We call these active galactic nuclei. The most luminous examples, quasars, are the brightest sustained objects in the observable universe. Some of them are visible from billions of light years away. The accretion disk is only part of the thermal picture. Many actively feeding black holes also produce jets. These are narrow, collimated beams of magnetized plasma launched from the poles of the black hole at speeds approaching 99.99% of the speed of light. The mechanism that creates these jets is still being worked out. The leading models involve the interaction between the spinning black hole, its magnetic field, and the inner accretion disk. What we do know is the result: relativistic streams of particles and energy that can extend for hundreds of thousands of light years, drilling through the host galaxy and out into intergalactic space. The effective temperatures inside these jets are difficult to pin down, precisely because the physics is relativistic, and the concept of temperature becomes complicated when particles are moving at nearly the speed of light. But estimates for the hottest regions within relativistic jets place them at tens of billions of degrees. These jets carry energy across distances that light itself takes hundreds of millennia to cross, depositing heat into the intergalactic medium as they go. A single jet from a single black hole can heat gas across a volume larger than a galaxy. That sentence is worth sitting with for a moment. One object, smaller than a solar system, projecting thermal influence across millions of light years. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy M87, about 55 million light-years from Earth. The glowing ring in that image is the accretion disk, material orbiting the black hole at relativistic speeds, heated to billions of degrees, emitting radiation across the electromagnetic spectrum. The dark center is the shadow of the event horizon itself, the boundary beyond which light cannot escape. That image captures both extremes in a single frame, the coldest possible object, surrounded by some of the hottest material in the universe. M87's central black hole also produces one of the most spectacular relativistic jets ever observed, a beam of plasma extending roughly 5,000 light-years from the galaxy's core. It's visible in optical light, radio waves, and X-rays. The particles in that jet are so energetic that they emit synchrotron radiation as they spiral around magnetic field lines, glowing across every wavelength we can detect. And the jet is actively shaping the gas environment of the entire Virgo cluster, the galaxy cluster to which M87 belongs. Now, there's another class of event I haven't mentioned yet that produces some of the most extreme temperatures in the known universe, and it's one of the most violent phenomena astrophysics has ever catalogued: gamma-ray bursts. A gamma-ray burst is a flash of the most energetic form of light in the universe, lasting anywhere from a fraction of a second to several minutes. In that brief window, a single burst can release more energy than the sun will emit in its entire lifetime. The two types, short and long, have different origins. Short gamma-ray bursts, lasting less than about 2 seconds, are now understood to come from neutron star mergers, the same events I described earlier. Long gamma-ray bursts, lasting seconds to minutes, are produced by a specific type of supernova called a collapsar, where a rapidly rotating massive star collapses and forms a black hole that immediately begins accreting the infalling stellar material, launching ultra-relativistic jets that punch through what remains of the star and out into space. The temperatures inside these jets are estimated at 10 billion degrees or more. The Lorentz factors, the relativistic speed multipliers, can exceed 100, meaning the material in the jet is moving at 99.995% of the speed of light. When these jets interact with the surrounding interstellar medium, they produce afterglows visible across the electromagnetic spectrum, from radio waves through X-rays, that can be detected from the other side of the observable universe. In March 2023, an extraordinary gamma-ray burst designated GRB 221009A, later nicknamed the Boat, the brightest of all time, was detected by multiple space-based observatories. It originated roughly 2.4 billion light-years from Earth. Despite that immense distance, the burst was so luminous that it temporarily saturated some detectors designed to measure the most extreme events in the cosmos. It disrupted Earth's ionosphere measurably, affecting radio communications from 2.4 billion light-years away. The total energy release is still being calculated, but early estimates placed it among the most powerful events observed in human history. If a gamma-ray burst of that magnitude occurred within a few thousand light-years of Earth, the radiation would strip our ozone layer and sterilize the surface. Life as we know it would end. Not from a collision, not from an impact, from temperature, from light so energetic, produced by material so hot that it would cook a planet's atmosphere from light years away. There's one more thermal environment I want to walk through before I bring this story to its conclusion, and it concerns the early universe itself. Because everything I've described so far, every stellar core, every supernova, every neutron star merger, every black hole jet, is just the universe replaying. In miniature, temperatures it lived through wholesale in its first moments. In the first second after the Big Bang, the universe was a sea of quark gluon plasma. Temperatures exceeded 1 trillion degrees. Matter, as we know, it did not exist. There were no atoms, no nuclei, no stable particles beyond the most fundamental constituents of nature, quarks, leptons, and the force-carrying particles that mediate their interactions. Everything was a single incandescent fog. Within the first microsecond, as the universe expanded and cooled, quarks condensed into protons and neutrons. This transition, called hadronization, is the same physics that the particle colliders at CERN and Brookhaven study when they create quark gluon plasma. The difference is scale. In the lab, it happens in a volume smaller than a proton. In the early universe, it happened everywhere, simultaneously, across the entirety of space. By about 1 second after the Big Bang, temperatures had dropped to roughly 10 billion degrees. Neutrinos decoupled from ordinary matter, streaming outward in all directions to form a cosmic neutrino background that still fills the universe today, though we haven't yet built instruments sensitive enough to detect it directly. Electrons and positrons annihilated in pairs, dumping their energy into photons and heating the photon bath relative to the neutrinos. Between 1 and 3 minutes, temperatures fell through the range of about 1 billion degrees to 100 million. This was the window for Big Bang nucleosynthesis, the brief period when conditions were just right for protons and neutrons to fuse into the lightest atomic nuclei: deuterium, helium-3, helium-4, and trace amounts of lithium-7. If the universe had been a little hotter, the nuclei would have been blasted apart. A little cooler, and the fusion reactions would have been too slow to produce anything before the window closed. The abundances of these elements, measured today in the oldest, most pristine gas clouds in the universe, match the theoretical predictions with remarkable accuracy. They are one of the strongest pieces of evidence that the Big Bang actually happened, and they depend entirely on the precise thermal history of the first few minutes. After nucleosynthesis, the universe spent the next 380,000 years as a hot, opaque fog of ionized gas. Photons couldn't travel far without bouncing off free electrons. Temperature slowly dropped from millions of degrees toward a few thousand. Then, when the temperature reached approximately 3,000 Kelvin, something remarkable happened. Electrons slowed enough to be captured by hydrogen and helium nuclei, forming neutral atoms for the first time. Photons, no longer constantly scattering off free charges, were released to travel freely across the cosmos. That flash of released light has been traveling ever since, stretched by the expansion of the universe from its original temperature of 3,000 degrees to its current 2.7 Kelvin. This is the cosmic microwave background, the same 2.7 degree figure I started with at the beginning. It is, in the most literal sense, the cooled down remnant of a moment when the entire universe was hotter than the surface of many stars. After recombination, the universe entered an era called the Cosmic Dark Ages, a period lasting a few 100 million years, during which no stars had yet formed. The gas cooled, drifted, clumped under gravity. Slowly, in the densest regions, hydrogen clouds collapsed under their own weight, compressed, heated, and ignited. The first stars, called Population 3 stars, are theorized to have been enormous, perhaps hundreds of times the mass of the Sun, burning at surface temperatures of 100,000 degrees or more, flooding the dark universe with ultraviolet light for the first time and ionizing the surrounding gas. These first stars lived fast, died as supernovae, and seeded the cosmos with the first heavy elements. None of them survive today. They burned out billions of years ago, but their thermal legacy is everywhere, in the heavy elements that make up the planets, in the reionized gas that fills intergalactic space, in the hot bubbles and filaments of the cosmic web. From the Planck temperature to the first stars, the universe's thermal history is a single, long, uneven exhale, each era defined by a temperature, each transition, from quarks to protons, from plasma to atoms, from darkness to light, triggered by the cosmos cooling past a critical threshold. We are living in the late, cool phase of that exhale, on a planet whose mild temperatures are so atypical of the universe's thermal norm that they amount to a statistical accident. Let me pull back from individual cataclysms now and talk about the big picture, because the thermal story of the cosmos isn't only about spectacular events. It's about where most of the heat in the universe actually lives, right now, constantly, with almost no one aware of it. For 3 decades, cosmologists struggled with an embarrassing bookkeeping problem. Measurements of the cosmic microwave background and the observed abundances of light elements, forged in the first minutes after the Big Bang, gave a precise prediction of how much ordinary baryonic matter the universe should contain. When astronomers added up everything they could find, the stars, the cold gas, the dust, the visible galaxies, the total came to roughly half of the expected amount. The other half was missing. Not dark matter, which is an entirely separate mystery. Just ordinary stuff, protons and neutrons, unaccounted for. The search lasted decades. The answer, assembled over the past 15 years through X-ray surveys, ultraviolet spectroscopy, and an elegant method using the dispersion of fast radio bursts to trace ionized gas density across intergalactic distances, is that the missing baryons were never missing. They were hiding in the largest structure in the universe, the cosmic web. The cosmic web is the scaffolding of the cosmos, a network of filaments and nodes that stretches across the entire observable universe, along which galaxies are strung like beads on invisible threads. Between the filaments lie enormous voids, regions of space, hundreds of millions of light years across, containing almost nothing. If you could zoom out far enough, far past superclusters and galaxy walls, the universe would look like a vast 3-dimensional web of glowing threads separated by darkness. Those threads are filled with hot gas, not cold molecular clouds waiting to form stars. Thin, diffuse plasma, heated to temperatures between 100,000 and 10 million degrees Celsius. This gas was heated by gravitational shocks over billions of years, as matter fell inward onto the filaments of the cosmic web, accelerating under gravity, colliding with itself, and converting kinetic energy into thermal energy. The result is the warm, hot, intergalactic medium, a nearly invisible reservoir of superheated gas that contains between 40 and 50% of all normal matter in the observable universe, nearly half of everything. Not in stars, not in planets, not in the cold interstellar medium, drifting in the spaces between galaxies at millions of degrees, too thin to glow in visible light, too diffuse for most telescopes to see, but absolutely, measurably real. The universe is mostly hot. The cold places we know, the rocky planets, the frozen moons, the icy comets, the dense molecular clouds, are the outliers, the anomalies. We live on one of them. We look up at a dark sky and assume the vast emptiness is cold. It isn't. Most of it is simmering at temperatures that would vaporize any known material. We just can't see it. Our eyes are tuned to visible light, and million-degree plasma doesn't bother with the visible spectrum. It radiates in ultraviolet and X-rays, wavelengths invisible to biological eyes, but blindingly bright to instruments designed to detect them. Orbiting X-ray telescopes like Chandra and XMM Newton have mapped this hot gas in galaxy clusters, where it's densest and easiest to observe. The intra-cluster medium, the gas filling the spaces between galaxies within a cluster, sits at temperatures of 10 to 100 million degrees. There's an enormous amount of it. In a typical massive galaxy cluster, the hot intracluster gas outweighs all the stars in all the galaxies of the cluster combined. The galaxies, those magnificent structures containing hundreds of billions of stars each, are the minority component of their own neighborhoods. The hot gas is the dominant form of ordinary matter. Much of that heating traces back to supermassive black holes. When a supermassive black hole at the center of a large galaxy actively feeds on surrounding gas, the material spirals inward through an accretion disk that heats up to millions of degrees. Many accreting black holes also launch relativistic jets from their poles, narrow beams of magnetized plasma moving at close to the speed of light, punching outward through the host galaxy and into the intracluster medium, depositing colossal amounts of energy along the way. One black hole, smaller than our solar system, heating gas across structures millions of light-years wide. The Perseus Galaxy Cluster, about 250 million light-years away, provides the clearest illustration. Its central supermassive black hole has been injecting energy into the surrounding hot gas for millions of years, inflating enormous bubble-like cavities approximately 200,000 light-years across. For reference, the Milky Way stretches about 100,000 light-years from edge to edge. This single black hole has blown cavities in the intracluster gas that are each bigger than our entire galaxy. The heated gas in those regions cannot cool efficiently enough to collapse into new stars, which means the black hole is functionally regulating the star formation rate of the entire cluster. Trillions of stars, hundreds of galaxies, and one compact object at the center, controlling their thermal fate through sheer energy output. This feedback mechanism, where black holes heat their environment enough to suppress cooling and star formation, is now recognized as one of the most important processes in the evolution of galaxies and galaxy clusters across the universe. The thermal output of objects smaller than our solar system shapes structures spanning millions of light-years. Temperature, at every scale, is the hand that steers the cosmos. Now, the ceiling. There is a maximum temperature, not a practical limit, not an engineering constraint, but a fundamental boundary written into the laws of physics. It's called the Planck temperature, and it sits at approximately 1.42 times 10 to the 32nd power Kelvin. About 142 million degrees. There's no useful analogy for that number, no way to ground it in human experience. It simply exceeds the reach of intuition by so many orders of magnitude that attempting a comparison insults the scale. At the Planck temperature, the thermal energy of a single particle becomes so extreme that quantum gravitational effects dominate everything. The wavelength of thermal radiation shrinks below the Planck length, the smallest meaningful distance in physics. General relativity and quantum mechanics, which already refuse to work together under even moderate conditions, break down completely. Every calculation returns results that have no physical interpretation. Physics, as a discipline, has nothing to say past that threshold. We believe the universe reached or approached the Planck temperature in the first instant after the Big Bang. Specifically, during the first Planck time, about 5.4 times 10 to the negative 44th seconds. There is no metaphor for how short that duration is. Comparing one Planck time to 1 second is like comparing the diameter of a proton to the width of the observable universe. It is a sliver of time so thin that calling it brief misrepresents reality by a factor that has no name. In that instant, everything that would eventually become every galaxy, star, planet, and person was compressed into a volume smaller than a subatomic particle, at a temperature that defines the outer edge of what science can describe. Everything since has been the universe cooling. Quarks condensed into protons and neutrons in the first microsecond. Protons and neutrons fused into atomic nuclei in the first 3 minutes. Neutral atoms formed after 380,000 years, when the temperature finally dropped below a few thousand degrees, low enough for electrons to settle into stable orbits around nuclei. That event released the cosmic microwave background, the faint afterglow we measure today, at 2.7 Kelvin. Gas collapsed into stars. Stars burned for millions or billions of years. Stars died, some quietly, some catastrophically. There remains seeded space with heavy elements. Planets coalesced from debris disks around new stars, and on at least one of those planets, in a temperature band roughly 100 degrees wide, between the freezing and boiling points of water. Chemistry became complex enough to generate molecules that could replicate themselves. Eventually, those replicating molecules assembled into organisms that could look up and wonder about what they were made of. Every atom in your body, heavier than hydrogen, was forged at temperatures exceeding 100 million degrees. The calcium in your bones was made in a dying star's core at roughly 1.5 billion degrees. The iron in your blood was the last element fused before a stellar core collapsed, formed at 2.7 billion degrees during the final day of a massive star's life. The gold in your ring, if you wear one, was produced in a neutron star collision at several 100 billion degrees. You are made of temperature. The extreme thermal violence of the universe is not something happening far away. It already happened billions of years ago, and the results are sitting in your chair. The endpoint of the universal cooling process has a name: the heat death of the universe. Not an explosion, not a collapse. The quietest possible ending. Trillions of years from now, the last red dwarfs, small, miserly stars that burn their hydrogen so slowly they can last for trillions of years, will finally exhaust their fuel and go dark. White dwarfs will cool into theoretical objects called black dwarfs, so cold they emit no detectable radiation. The universe is not yet old enough for any black dwarfs to exist, and won't be for an almost inconceivable span of time. The last black holes, the supermassive ones, will slowly evaporate through Hawking radiation, over timescales so long that the current age of the universe, 13.8 billion years, vanishes into irrelevance beside them. When the final black hole evaporates, what remains will be a faint, perfectly uniform bath of extremely low-energy photons and orphaned subatomic particles, spread across a void so enormous that no two particles will ever interact again. Not absolute zero, just infinitesimally above it. A final whisper of warmth, the last echo of a moment when everything was one point, at a temperature physics has no language for. Let me end with something tangible, something you can look at tonight. The James Webb Space Telescope sits at the second Lagrange point, 1.5 million kilometers from Earth, observing the cosmos in infrared at an operating temperature of negative 233 degrees Celsius. To detect the faint, ancient light of the first galaxies, its instruments must be colder than nearly anything in the solar system. A sunshield the size of a tennis court, 5 layers of reflective Kapton film thinner than a human hair, separates the sun-facing side at 85 degrees Celsius from the instrument side at negative 233. Over 300 degrees of difference, separated by a few meters of foil and the emptiness of space. That sunshield is the thermal story of the universe in miniature. Scorching radiation pouring in from one direction, the deep cold of the void on the other, and in the narrow gap between, a fragile instrument seeing farther than anything we've ever built. We live on a version of that shield. Our atmosphere, our magnetic field, the churning iron core beneath our feet that powers the magnetosphere. These are the layers separating us from a star that burns at millions of degrees on one side and the cold vacuum of interstellar space on the other. A few hundred kilometers of nitrogen and oxygen and a magnetic cocoon powered by liquid metal are all that stand between you and an environment that will kill you with heat or cold, depending on which way you happen to be facing. The total habitable temperature range on Earth, roughly negative 90 to positive 60 degrees Celsius, is a window of about 150 degrees. The universe's thermal spectrum spans from near absolute zero to 142 million degrees. Our window isn't a band, it's a crack, a hairline fracture in the thermal fabric of reality, and everything human beings have ever been has managed to exist inside it. The universe is not cold. It never was. It is a thermal landscape of extraordinary violence and scale, where individual events routinely produce temperatures that dissolve the structure of matter, and where the bulk of ordinary material between galaxies sits quietly at millions of degrees, invisible to human eyes, but blindingly bright to the instruments we've been clever enough to build. The cold, dark emptiness we see when we look up at night.